Okay, so we have two 3-foot long shafts. They are both made of steel. They also both have the same diameter. They're connected to the gears and fixed at their ends. So at A and B we have a wall. It's supported by bearings at C and D, which allow free rotation. We have an applied torque right here of 600 pound-feet. We want to find the maximum shear stress in each shaft. So to do that, we have to find the actual torsion in each shaft. We'll call it shaft A and shaft B. So first step, as always, draw a free body diagram. So I'm going to split these up. So this top shaft, we have a applied at the end here, 600 pound-feet. Then it's fixed at wall A. All of these reaction forces have to be resisting the applied force. So we know it's going to go the opposite direction. I'll call that torque A. Then there's also going to be a force between the two gears here that will also be resisting. So if we're trying to twist it in the, say, clockwise direction, that means the force has to be pushing. So if this is our gear, our force is pushing against that torque. And we'll just call that force F. So that's all my forces here. I would technically maybe also have a supporting force at C, but that doesn't matter for the torque, so we don't need that. And I'll call that free body diagram 1. In free body diagram 2, it's going to be this bottom shaft. So again, we have a smaller gear. We still have this force that's between the two of the gears. It's going to be an internal force, so it's equal and opposite. It's pushing to the right on this side, so it has to be pushing to the left on the top of this gear. And then we know at the wall, it has to be resisting the other forces. So as this force turns the shaft, say, counterclockwise, the wall then has to go the opposite way. And I'll call that T sub B. So we have torque A, torque B, and force F. We have 3 unknowns here, but only 2 free body diagrams. So the first step is normally just statics. Before we do that, we want to find the maximum shear stress. And normally stresses are given in KSI. So I'm going to go and convert that 600 pound-feet to kip inch. So 600 pound-feet in 1,000 pounds, there's 1 kip. And in 1 foot, there is 12 inches. So that gives us 7.2 kip inch. So now we can do statics. We know that the system is not moving, it is stable. So from free body diagram 1, we can sum torque, which is really just the same as saying summing moments about the axis along the shaft. And using right-hand rule, I'm calling that direction positive. And it's static, so it's going to equal 0. So we have a positive TA. We have a negative, this rotation here, which we said is 7.2. And then we have this force that's being applied. So plus force times the distance. We're given the radius is 6 inches. So F times 6. So we would get T sub A equals 7.2 minus 6F. Then we can do the same thing for free body diagram 2. So from free body diagram 2, it's important to declare where you're summing torque. And again, I'm going to say this direction and right-hand rule is positive. So we have a negative TB plus the radius of this gear is 2 inches, so 2 times F. So we get TB equals 2F. So that's all the statics we can do here. So we have 2 equations, but 3 unknowns. So we need one more equation to solve this system. So one thing we do know is that their angle of twists are related, because those gears are connected. So you do the radius of 1 times the angle of twist of 1 equals radius 2 times the angle of twist 2. You can use diameter, circumference, doesn't matter, the terms cancel out. But just some dimension, so radius, diameter, circumference times the angle of twist equals the same thing, but for the other gear. So we'll call this top gear, gear 1, this bottom, gear 2. So the first radius is 6 inches times the angle of twist. Instead of putting 1, I'll put A, because that is for shaft A, equals the radius of the second one is 2 times the angle of twist of shaft B. So that means we know that 3 times the angle of twist A equals angle of twist B. We're given the equation for angle of twist equals TL over JG. That assumes that we do not yield. So once we're done with this, we'll have to prove that we don't yield to make sure our results are valid. So plugging that in, we get 3 times TL over JG of A equals TL over JG of B. Now if you remember up here, both the shafts are made out of steel and they both have the same diameter. So that means our J's and our G's are the same, so they cancel out. Both of the shafts are the same length, so those cancel out. So we're left with 3 times TA equals TB. Then from there, we just have a system of equations. So we can plug that in for this equation up here. So we said T sub A equals 7.2 minus 6F. And our other equation right here, well, is T sub B equals 2F. So we don't really care about the force F, so I'm going to go ahead and solve that one out. So this equation is the same as saying F equals T sub B divided by 2. I'm going to plug that in over here. So we get TA equals 7.2 minus 6 times TB over 2. And we said TB equals 3TA. So TA equals 7.2 minus 6 times 3TA divided by 2. So solving that, we get TA equals 0.72 kilopinch. And then plugging that back in, we get T sub B equals 3 times that, so 2.16 kilopinch. So again, we have to make sure that they don't yield. So because if they were like a different material or different length or something, or not length, but a different diameter, we would have to check both. But because they're the same shafts, we can just choose whatever value is highest. And if that one doesn't yield, then the first one won't yield either. So it's in torsion, it's a shear stress. So shear equals T rho over J. We said our torque is 2.16. Rho, the area with the highest stress, is going to be the outer radius, which is 0.75. Divided by J, that's going to be pi over 2 times 0.75 to the fourth. And that gives us 3.26 KSI. Now it says our material is steel. Steel shear yield is at 21 KSI. We are less than 21. Does not yield. We are good. And that is our answer.